Hello everyone, here is a situation. We have a plane in three-dimensional space and a line intersecting that plane at a particular point. Our goal is to compute the coordinates of that point using three levels of difficulty. On the first level, we are going to use just basic algebra. On the second level, we are going to use vector notation, and finally, at the third level, we are going to set up a system of equations to find those coordinates. So let's see. The first step of the easy difficulty, we start by writing the equation of the plane. The general equation of the plane is given by ax plus b of y plus cz plus d is equal to 0. If you supply me with the constants a, b, c, and d, that determines a plane in three-dimensional space. The equation of the line is in fact three equations given by x is equal to x0 plus v of x times t, y is equal to y0 plus v of y times t, and z is equal to z0 plus vz times t. If you supply me with the constants x0, y0, z0, and the v's, that determine a line in three-dimensional space, because as t here, the variable t, ranges over the entire real numbers, the points whose coordinates are of the form given by this, given by this, and given by this, they cover the entire line. And so, going back to our original problem, the point of intersection between the plane and the line must obey the equation of the plane, and its coordinates must have the form given by this. Okay? And so I'm going to substitute this thing here. It gives me a times something plus b times something plus c times something plus d is equal to 0. But in this case, that something is not the xy coordinate of any point on the plane. It must be specifically a point whose coordinates are of this form. So a times x0 plus vx times t, b times y0 plus v of y times t, and c must multiply z0 plus v of z times t. This expression now can be solved for t, giving us the following result. So we have t equal to something. So we find here the numerator, ax0 plus b of y 0 plus c z0 plus d, with a minus sign, and in the denominator we find a vx plus b vy plus c vz. And notice t now is related to the parameters that determine the line on the plane, and that t is unique. After we have computed t from the parameters, we can go back to the equation of the line and substitute here, giving us the coordinates x, y, and z, which will be at the intersection coordinates between the plane and the line. At the intermediate level, let's use vector notation to describe the plane. A plane requires two ingredients: a vector on the plane, meaning a vector that starts at the origin and lands with a tip on the plane, and the second ingredient is a vector perpendicular to that plane, like the n vector here. It will be useful to consider n to be a unit vector, meaning with length 1. We also find in this picture a line, and to describe a line we need two ingredients: a vector starting at the origin and landing on the line, r0, and a vector parallel to that line. Looking at the plane, we notice that any two vectors that land on the plane, their difference is always orthogonal to the vector n, and this allows us to write the equation of the plane as follows. We dot n with the difference between r minus r1, and as long as the vector r lands on the plane, this dot product must be equal to 0. And so the plane is a set of vectors r that, when substituted here, make this statement true. The equation of the line is given as follows: is the set of vectors r which have the form r0 plus v times t. It will be useful to think of R0 as the initial position vector whose components come in units of meters, and V as the velocity vector whose components are in meters per second. With this interpretation, then, V times t would be the displacement vector that you must add to R0 after t seconds have elapsed. Now, looking at a plane and a line, we are looking for a vector r that obeys this equation and is of the form given here. And so we are going to substitute n dotted with something minus r1 is equal to 0, where that something is not just any vector landing on the plane, is a vector of this form. So r0 plus v times t. We can now use this equation, rearrange it, and solve it for t. Using the distributive law, we find n dotted with r0 minus r1 plus n dotted with v times t is equal to 0, where we note that this thing here and this thing here are numbers. So this is a trivial equation to solve. We get the following result. T must be equal to the following ratio. N dotted with r0 minus r1 divided by n dotted with v, with a minus sign because this thing moved to the other side. Now that we have a formula for t, let's understand the meaning of this calculation. Note that in mathematics, every single time we want to understand the meaning of a formula, we first try to understand the meaning of each part of it. So, let's start by understanding what does it mean r0 minus r1. Going back to the picture, we see that it is the vector that starts at r1 and ends at r0. Okay, this is the first part. The second step, let's understand the dot product of this difference with n. But recall that n is a unit vector, and also that the dot product between any vector with a unit vector will give you the projection of that vector along the unit vector. So in this case, r0 minus r1 dotted with n gives me the projection of this vector along n, meaning it is this length here that starts at r0 and goes straight down until it's the plane. So it is the distance in meters. Let's now try to understand the meaning of the denominator. The denominator is also a projection of the velocity vector along n, meaning it is this length, which comes in units of meters per second. To understand better the meaning of these projections, let's imagine that we are at r0 moving along the pink line at velocity v. Then our shadow along n will move this distance at velocity given by this projection. And so the ratio of this numerator and denominator will give me the time taken by the shadow to move from r0 up to this point, which is the same as the time that it takes me from moving from r0 up to the intersection point. As a result, from this time t, now we can go back to this formula, substitute that t here, and it will give us from the initial position the current position, which is r, the intersection point. It is useful to compare the formula we just derived for t with the previous one. So let's go back to our formula and rewrite it as follows. The minus sign stays, so it's n dotted with r0 minus n dotted with r1. And in the denominator we find the same thing, n dotted with v. Our previous formula is given by this. Here, comparing, we find that this part, the projection of r0 along n, is found here. Okay? Where the components of n is a, b, and c. The projection of r1 along n with a minus sign is found here. It's a d. Okay? And the denominator, well, we find here the coordinates for n, here a, b, and c, and the coordinates for v, here vx, vy, and vz. Our third level of difficulty, requires us to look at the problem with new eyes. Looking back at the plane and the intersecting line, we focus on the line and realize that the line is no more than the intersection of two different planes. So our goal with this third approach is to find the equations for those two planes. So let's see. We have here our plane alpha, which is described by one vector r1 and one perpendicular vector. Those two determine the plane alpha. We also find here the pink line, which is described by the vector r0 and the parallel vector v. The intersection of the line and the plane alpha is this point here. On the figure, you also see two planes, alpha prime and alpha double prime, whose intersection gives us the pink line. We want the equations for those two planes. And for those, what ingredients do we need? Well, we need a point on those planes and a perpendicular vector. Looking back at the picture, we notice that r0 is common to both planes, so we can use it as a starting point. So what is left for us is to find the perpendicular vector on n prime and n double prime. And for that, we note that n prime and n double prime are perpendicular to the velocity vector v. Those perpendicular vectors that we seek are the solutions n, which when dotted with v are equal to 0, or in components, mx dotted with vx plus my dotted with vy plus mz dotted with vz are equal to 0. This equation has three unknowns, and so there are many solutions for it. As you can see from the following picture, the vector v has many orthogonal vectors. I'm going to introduce additional constraints on top of this equation so that my life is easier in finding those solutions. For example, consider that mz is equal to 0. That renders this term equal to 0, and so what I'm left with is to finding mx and my such that this thing is equal to 0. But you see, that's easy, because we can actually guess the answer. By setting mx is equal to v of y and my is equal to v of x, well, we just found an answer. So we set this thing to equals to n prime z, this thing to nx prime, and this thing ny prime. Okay? Here it is an answer. We want now to find a different perpendicular vector, and so let's introduce a different constraint by setting, for example, mx is equal to 0. By doing so, mx is equal to 0, that implies immediately that we can guess that my is equal to minus v of z, and mz is equal to v of y. As a result, we can set this nx double prime, this thing ny double prime, and finally this and n double prime z. With those two perpendicular vectors in our hands, we can now write the equations for the planes. Alpha prime, which is n prime, which when dotted with r minus r0 is equal to 0. The plane alpha double prime, which is n double prime we just found, r minus r0 is equal to 0. On top of this, we add the original plane, alpha, which is n dotted with r minus r1 is equal to 0. And finally, we arrived at a system of three equations in three unknowns, the unknowns being the three components of the vector r. This system represents the intersection of these three planes, and the solution r are the coordinates of exactly this point. Now that we have the three methods, I challenge you to follow them using numbers. You just choose the numbers for the components, for the vectors and the plane, and you just follow three different paths and try to see if you can get exactly the same answer in three distinct ways. I wish you good luck and see you next lecture. Goodbye.